this is what was circulated around. I'm going to talk about DeSitter space. This talk's going to be essentially all pure mathematics, geometry, pure geometry. This is space, a lovely space that everybody should know about. Because it's the first space you trip over when you try and get away from Minkowski space and you're trying to do general relativity of any kind, it was found very early. Willem de Sitter found it in 1917, just when Einstein was finishing his general relativity theory. Einstein didn't like that. He really didn't like having anybody else on his patch. And he didn't like it and found things that were wrong with it and so on. But anyway, Einstein, we have to live with Einstein. For a long time, well, and still now, it's regarded as a curiosity. But one of the problems with it was that there was a very influential mathematician called Hermann Weyl who proposed something called a coherency postulate, which says that things can't appear suddenly. And that means that when you look at DeSitter space, you only get half of it. But if you go back to taking the whole of DeSitter space, you get something that really does fit with all the modern observations. And I think it is basically what the universe is. Though of course, you've got to make adjustments to it. I'll be talking about some of those anyway. Okay, so the catalogue of lost opportunities, because we could have had the right model for the universe right from the beginning, no Big Bang, none of the rubbish. Okay, let's go on. So the most elegant description of DeSitter space, it's the analog of a sphere in Minkowski space. So Minkowski space is flat space for special relativity. It has a metric, ds squared minus dt squared. That's the time coordinate plus space coordinates. And I've got Minkowski 5 space because I want a 4-dimensional manifold for space-time. So I want a sphere in Minkowski 5 space. So you take the points in Minkowski 5 space, which are a unit distance, a distance a from the origin. And there it is. That's the equation of DeSitter space. So A is the radius of DeSitter space. You can think of it as the radius of the universe. And what this space is, it's a solution of Einstein's equations, vacuum equations, with a positive cosmological constant, lambda equals 3 over a squared. And just by looking at it, you can picture it as a hyperboloid. So there's some lovely pictures I picked up from a paper by Moschella in the seminar Poincaré 1. I've got the thing down the bottom there. And so these are in the wrong dimension because you get the whole picture, by the way, because my screen might not fit in your screen.
Yes.
Yes, so it starts with that in special relativity and goes down to DeSitter metric, right? Okay, so it's a hyperboloid. You've got time going upwards and space going round. Okay, the dimension that's illustrated, space is 1-dimensional. But you have to think of this circle around here as being a 3-sphere, and it broadens out upwards and downwards. And the picture is a wrong metric. The metric's all wrong. If you take a slice through, vertical slice through it, it's ordinary special relativity in 2 dimensions you may be familiar with, where you have time and space, and you can move along hyperbole. So this hyperbola here, you can move along it. Okay. So these are hyperbolic rotations or shears, and the formula is cosh x, sine x, cosh x as a matrix. It's just straightforward hyperbolic rotation. And if you know any special relativity, that's one of the standard isometries in special relativity. Okay, so you can move by an isometry, you can move any point up this hyperbola. So if you go over to this picture here, I'll tell what this picture is about in a minute. You've got a circle in the middle, and a shear will take it up to any other one of these ellipses. So this is the circle is the intersection of a plane through the origin with the hyperboloid, and the ellipses are intersections, sorry, the horizontal plane with other planes through the same line across here. So they're all equivalent in the DeSitter space. Okay, and then of course you've got the horizontal rotations using the symmetry of the three sphere. In this picture here, you've got one sphere, but you can rotate. So you've got one set of rotations. They're like boosts in, if you know Lorentz group, they're the velocity motions, and these are the rotation motions. Okay, so let's go on. So as I said, the picture doesn't give the correct metric, but it gives you a very good idea of the linear structure of the DeSitter space. I'll go back to it for a minute. You've got all the planes through the origin, all the spaces through the origin, because you've got to think of this as being four-dimensional, not two-dimensional. All the hyperplanes, planes and hyperplanes through the origin. And they're intersecting the DeSitter space in various things, which are straight lines in DeSitter space. Although it looks curved, it isn't. It's straight. It's like if you do any special relativity, things that don't look like they are. And you've got built into DeSitter space, or into this picture, you've got projective geometry, because all the stuff through the origin, that's the definition of projective space, lines through the origin. And you've also got hyperbolic geometry. If you take the other hyperboloid, the one that is minus a squared instead of a squared, and then you intersect with that, you get what's called hyperbolic space, non-Euclidean space. So it's all built in. Okay, so the picture doesn't give a good idea of the metric, but it gives a very good idea of the linear structure. Geodesics are given by planes through the origin, geodesic 2 spaces by 3 spaces, etc. So if we go back there, the left picture shows the expanding frame based on, let's think of this line up the middle here as being the home geodesic. That's where we're traveling, okay? And all the other blue geodesics here are all going converging to it at minus infinity. And so that's this, and in fact, if you take these horizontal things, they look curved, but in fact, they're absolutely flat. They're Euclidean flat spaces. These are all Euclidean flat spaces. And as you move up, the motion is exponential expansion. So you've got a built-in Hubble space here with expansion. It's just built in. Okay, now let's have a quick look. Let's see what else I want to say on this picture here. Okay, go on. So, okay, so time's upwards, expansion's upwards. This is a picture of the DeSitter metric, and this is how DeSitter actually defines his space with the metric that does this. So he's got a central geodesic. All these other lines are not geodesics. They're not intersections of planes with the thing. These horizons are, but he had the idea that the space was confined between these space horizons, and he had the idea that everything moves upwards along these non-geodesics. And the spaces that go across it, are they flat? No, they're not flat, because these are the flat spaces. So that you've got a very unnatural way of thinking of it. So, and that's his metric, these coordinates I've got there. So the right picture shows a DeSitter metric with horizontal geodesics, black ellipses. Oh, they are geodesics. Yes, of course they are. They're intersections with planes in the origin. Sorry, I said they weren't, but they are. And the transverse time-like flow lines, orange, for which only one, the center one, is a geodesic. So although it's a static metric, the time-like flow is very unnatural. A natural flow would flow along geodesics. So it's a very unhappy choice for the first metric for space, and people just missed its beautiful symmetry. It's perfectly symmetrical. It's as symmetrical as the fourth space. It has a 10-dimensional symmetry group. Light paths in Minkowski space are straight lines at 45 degrees to the vertical, just like in special relativity. And light paths are those light paths in Minkowski space that lie in the hyperboloid. So this is a picture for that. Again, pinched from Michelle. He's produced beautiful pictures for us. Oops, I did the wrong thing. I'm trying to get it small. So this is, the blue is light cone in Minkowski space, and it intersects the DeSitter space in the light cone in DeSitter space, which in this picture is two lines, one here and one there. You'll have to imagine all this. It's very difficult to see it. Okay. Oops. Not yet. Let's get back. Okay, so the light paths are straight lines at 45 degrees to the vertical. Light paths in DeSitter space are light paths in Minkowski space that lie in the hyperboloid. And that's the figure we just looked at. And if you think projectively, a forward light line, so that's one upwards, sorry, I've gone the wrong way. Forward light line, that's one going upwards, is in fact a tangent to the sphere at infinity. If you're sitting at the origin looking outwards, you see a sphere up here, and the light lines are tangent to it. Okay, so that projected picture will come back. Okay. And there's a similar, sorry, I keep moving the wrong way. There's a similar sphere at the bottom for the negative light lines, and I'm going backwards in space. Okay, so we're ready to move on. Okay, so now here's Hermann Weyl's coherency postulate. 1923, also very early. It's amazing how much stuff was done very early. His postulate is that no astronomical object can suddenly appear into view or has so appeared at a finite time in the past. They must always have been divisible. So that means that if you go back to DeSitter space, I'll go all the way back to here. I should have a way of jumping to these, but never mind. It's at the Shotwell viewer is a very nice viewer in some ways, but it doesn't allow you to jump around. Okay, so everything's visible. What you can see backwards in time is constrained by the lines that are parallel to your home geodesic going backwards in time. So everything that's allowed by Weyl's postulate lies within this thing that I've indicated with blue lines here. And that's the expanding frame. Okay, I explained everything was expanding upward. And it goes down to a point at minus infinity. So what Weyl has done is to cut out all the stuff that's going the other way, losing half the symmetry, losing the symmetry between forwards and backwards. So that's the effect of Weyl's hypothesis. Okay. So the blue lines are geodesics in which objects permitted by Weyl's hypothesis are traveling, with the central one being the home geodesics. And the black lines are the transverse flat space sizes, as I said before. And so you've got something that's very close to the standard model. In fact, it is one of the, whatever they're called, Friedmann Lemaitre metrics, the one with the constant expansion. Okay. Now, if you know anything about hyperbolic geometry, you know that geodesics that go off to infinity go miles apart. They go whizzing off and exponentially far apart. Nothing stays close. If you stay close to a geodesic, you tend to infinity at the same point. So if you've got two geodesics which are not essentially the same, in other words, not extensions of the same geodesic interval, and they don't, I've left out a phrase here, and they don't come from the same point in minus infinity, then they always move apart in positive time at an increasing rate, which rapidly tends to exponential separation. So this is exactly what happens in the standard model, where all geodesics allowed by Weyl's postulate move apart at all times. But the standard model starts with the Big Bang singularity and is very unsymmetrical. So thus, although perfectly symmetrical and having no Big Bang singularity, expansion is built into DeSitter space. So the idea that expansion means a Big Bang is just wrong. Here's an example. Here's a space which has expansion and no Big Bang. Now, there's a very interesting fact that follows from this. If you take two observers, A and B, moving on different geodesics and not converging to the same point at plus infinity, I left that out by mistake. Since they eventually move apart faster than the speed of light, communication stops. There's a definite time B star for observer B, after which a light path from B cannot reach A. But A does not see that happening. A sees B forever in its own time. B appears to be moving away faster and faster, getting more and more redshift. The moment B star, when B goes out of contact, appears to A to be plus infinity. So I've drawn a picture for this. So you've really got to understand this picture because it explains how it all works. Okay, so we're looking at the right-hand picture here. I've got two pictures here. I couldn't be bothered to redraw them separately. Okay, so you've got to think we are A, and this is our home geodesic. B is another galaxy or another astronomical object moving on a geodesic. I've drawn a projective picture. So I brought infinity down to a finite circle. Actually, you can do that in projective geometry. You can think of the line of infinity as a draw it in the middle of the plane. So what I've done is to project the picture from a point from the origin onto a plane. Okay, so this is S plus. This is the sphere at plus infinity. And a light path is a tangent to that sphere. So this here, I don't know why it's come out as it seems to have come out as a hand instead of a pointer. This is the light path from a point on this geodesic that we're looking at coming to us. So we see it here, right? And we carry on seeing it all the way up to until it gets to B star. At B star, the light path is tangent to the sphere at the point where we're going to get there. But that's plus infinity for us. We never get there. So we never see B star. All we see is the light we're looking at, the galaxy we're looking at, moving all the way along from B to B star, getting slower and slower and slower in our time and never actually getting there. We see it forever, but it seems to be getting slower and slower. Okay, so this is a description of that. Picture in figure 3, that's one we've just been looking at. They're projected pictures in which the light spheres, which are at infinity in DeSitter space, are represented by finite spheres, and geodesics are represented by straight lines with null geodesics tangent to the light spheres. S plus is the forward light sphere, and S plus will come down in a minute, the backward light sphere. And you can think of these pictures obtained by projecting from the origin in Minkowski space onto a hyperplane not through the origin, a typical projected transformation. In the pictures, a typical light path from B to A, leaving B at time B and arriving at A at time A is shown. I just illustrated that there. That's the typical light path there. In the right-hand picture, the time B star for B is the time when the light cone from B meets S plus, where A meets it. And after this, the future of B does not contain any points of A. Communication ceases. For A, this happens at time plus infinity. So let's go on. The dual effect, going backwards in time, is the first encounter illustrated on the left. So let's go back to that. Blow it up, move it into the screen. If we can. So this is the first encounter now. So now we're down at the bottom light sphere. So this is where light is backwards, in backwards time, where the light are coming from. So once again, we've got A, this is us, we're on the home geodesic, and B is something we're looking at. And a typical point on B, the light path coming from B to A, coming away from the S minus towards S plus, which isn't in this picture. Okay. And there's a point A star here when the light paths going backwards from A pass our tangent to S minus at the point where B, it's minus infinity on the geodesic for B. So what's happening? As we're moving along here, we don't see B at all. There's a point at which we start to see B there suddenly. But what happens is that very, very quickly, all the light from B going back to time minus infinity all arrives all at once. So we get an enormous flash of very, very high frequency light. Okay, so this is the coming into our universe, actually becoming visible. At the point when it becomes visible to us, we get an enormous flash of extremely high frequency light. Okay, well, you might have met that before. So this is happening at, sorry, it's the wrong description. Yeah. Okay, so in a very short period of A's time, B bursts over A's horizon, and the entire history back to minus infinity is seen by A. The dual of the infinite redshift at time infinity is an infinite blue shift at time minus infinity. The energy received by A is a burst of energy starting in high gamma ray band, rapidly dropping to ordinary light waves and radio waves. And this is what a gamma ray burst is. So this is quantitative to observe gamma ray bursts. And Robert Markay and I have been selling this theory for some time now, and we can't get it published in a respectable journal. It's such simple geometry. It's very easy to do the geometry and get it right. And we had to publish it. Oh, it's a nice journal, Palestinian Journal of Mathematics, very good guys, and they published it for us. But it ought to be in one of the best astronomical journals, astrophysical journals. But they just say, oh, well, we know what gamma ray bursts are. You're wrong. And that's the end of it. Anyway, oh dear, on my webpage, it's on my webpage. So you can pick up this paper from my webpage, and it's also appendix to the book, a shorter version's appendix to the book. Okay, I might get back to these ideas later, but my time's going quite fast, so we'll press on. Okay, now, this is a wonderful symmetry of DeSitter space. It's duality. Go backwards in time, it's going the opposite of what it's going forwards in time. So there's a dual effect for backwards time. Backward geodesics separate exponentially, and there's a contracting frame based on any time-like geodesic, consisting of geodesics to converge to it in forward time. So if you remember that picture, figure 1, that was the big blue picture being this. Take the left-hand picture, that's the one that showed what you can see under Weyl's hypothesis. Turn it upside down, and you get the contracting frame based on the Hermann geodesic. So you've got contraction built in. So DeSitter space has expansion and contraction built in. You don't, they're just there, and they fit together perfectly. It's like, I mean, Escher knew all of this. Expansion and contraction fit together perfectly. Okay, now we're going to explain redshift, because the whole point is we're trying to make a theory with no Big Bang. Most people think that because there's redshift, there has to be a Big Bang. Well, anyway, we've got to explain redshift. Okay, so A, as I said, is our home geodesic. B is another geodesic on which a light source, typically a galaxy, is traveling. Assume B is not gravitationally bound to our galaxy, in other words, not to our local group. So that means it's moving apart. And then what happens is there's a short period with a gamma ray burst starting at time A star. That was in the left-hand picture. Let's just quickly whiz them up again. So there's pictures here. So typically it starts here with a flash of B star, and then at A star for us, and it goes on to B star for it, and then we don't see it anymore. It gets redder and redder and redder. Okay, and this is all just geometry of DeSitter space. There's no physics here at all. Okay, so assume that A is our home geodesic, B is another geodesic. Assume B is not gravitational bound, not part of the local group. In other words, it's not going to infinity with us. Typically, there's a short period starting with a gamma ray burst at time A star, when we see the light from B blue shifted, and B appears to be traveling towards us. Then the blue shift decreases and gets replaced by redshift. The galaxy appears to come as close to us as it can and move steadily away. The key behavior is this. The blue shift period is typically very short. In fact, it can be arbitrarily short. The movement away rapidly tends towards exponential separation and exact Hubble law. And we see this phase the entire remaining lifetime of the universe, which in DeSitter space is for an infinite time. Later on, I'll explain that we're really not in DeSitter space and that time is actually finite for what we can see. That we don't see more than about one Hubble distance, but that's part of a different story. At the moment, let's just sit with DeSitter space. So it's infinite time. So here's a mathematical plot showing exactly what happens in DeSitter space. Okay, so this is the redshift is up here, and it's blue shift to begin with, and then it goes very rapidly to straight line, perfect Hubble law. Goes on then forever and ever. Okay, so now assume we've got a uniform distribution of light sources in the DeSitter universe that we're living in now, and they're radiating to us from other geodesics. All but a tiny number appear to be traveling away from us and to fit closely to an exact Hubble law, because we see the ones traveling away for infinite time. The ones coming to us for a short time. So you get the short blue shift and the infinite red shift. So almost all, in a measured theoretical sense, are close to an exact Hubble law. So when you do a survey, you naturally ignore the few exceptions as outliers. There's something gone wrong. We've got a funny one here. We'll just ignore that. And you decide that all light sources are on the Hubble law, and the whole universe is expanding. An extreme example of observer selection bias. We ignore the evidence that the universe is also contracting because it's so slight in comparison to the evidence it's expanding. Indeed, most of the energy coming from incoming sources, the contracting bit, arrives in the form of gamma ray bursts, as I explained, and as we've seen shortly, as the energy that gets thermalized and seen by us as the cosmic microwave background. Neither of these is thought to be anything to do with expansion or contraction. So we think it's expanding, but it's also contracting. In fact, the universe is in a steady state, and the expansion is a grand illusion. Okay, and that's just DeSitter space. I haven't got any physics here, it's just geometry so far. Okay, now there was a perfectly Copernican, so you've seen it's perfectly Copernican. Oh, I didn't explain the transitivity, never mind. I'd too like to go back now. So there's the steady state theory, SST, propagated by Hoyle mostly, Bondy-Gold-Hoyle steady state theory. The incoming matter that balances expansion, so the contraction, the stuff that causes the contraction, is not created as it is in the steady state theory. The idea was that the universe creates matter. It does not appear from nowhere. It's in the universe all along. It's just that we don't see it. There's a similar incompleteness for forward time in both DeSitter space and in the standard Big Bang model. Although a galaxy appears to us to be there forever and getting further away and more redshift, in fact, it goes out of contact in a finite time in its own frame. This view makes it clear that the standard model is incomplete. It's only the forward half of the picture. I've left out the backward half. That's what Weyl did, threw away the backward stuff. Okay, this observer selection bias was proposed by Robert Mackay during the collaboration we were doing on a paper for Redshift. And though we didn't actually use it in the paper we published, it's now my view, and Robert's view too, that it's the key idea for the correct explanation of Redshift, which I've given you today. Okay, now I think it's time for a bit of hot news. So this is science news. This, well, actually, it's a few months old now. Debate over the universe expansion may unravel physics. Is it a crisis? There's a crisis in physics. Okay, so this is newspaper stuff, red top stuff, actually blue top here. Okay. One technique for measuring the current expansion of the universe is taking a baby picture of the cosmos and extrapolating. The infant image is the cosmic microwave background. This is under standard theory. Light emitted just after the Big Bang. To translate the information to expansion rates of the modern day universe, scientists use a standard cosmological model to make a prediction. And what comes out, using the Planck data, is that the universe is expanding at the rate of 67.4 kilometers per second for each megaparsec, about 3 million light years of distance between objects. And the stuff is so accurate now. They've got this cosmic microwave background so precise. They know the experimental error is only 0.5 kilometers per second per megaparsec. So that's somewhere between 66.9 and 67.9. But there's these wonderful supernova measurements measuring redshift from the light that's coming to us. And they settled on a larger expansion rate of 74.0. And again, they're so good now that they've got very, very small experimental error. So now look at it. You've got between 66.9 and 67.9, or between 70, I can't do it, 72.6 on 75.4. And they're not the same. They're out. It's about 3, you know, I think you're down to the 1 in a million is wrong. Okay, so the standard model is wrong. Okay, anyway, I'll come back to that and explain what's going on here later. Okay, now, we've just mentioned the cosmic microwave background, and we've got to explain the cosmic microwave background because it's the trump card for the Big Bang. The cosmic microwave background was forecast because we should be able to see the Big Bang radiation buzzing around still, and it will have got quite cold, and in fact temperatures around 2.7 degrees Kelvin, not centigrade. And they found it. So that proved the Big Bang. So at that point, everybody said, wonderful, we've got absolutely proved it. I mean, the fact that there's other explanations for it didn't occur to them. Anyway, so it's the trump card, so I can't get through to anybody unless I have a proper theory for the cosmic microwave background. And that's what I'm going to show you next. Okay, so it's a highly isotropic thermal radiation field that appears to emanate from every part of the sky. In particular, it comes from the apparently dark background where there are no visible stars or galaxies. I call that the dark horizon. It's thermal to better than 1 part in 10 to the 5th, has a temperature between 2.725 and 2.726. They got it very, very, very accurate. That's how they got the expansion so accurate. It's apparently anchored in the Machian rest frame determined by distant galaxies. The point is that the motion of the Earth can be measured with respect to the cosmic microwave background frame, and it's about 371 kilometers per second towards the Leo. And when I say Machian rest frame, I'm pretending that it exists, but this is just the description that is given when you read the literature. If you look in Wiki, for example, and there's small fluctuations in temperature, which under the standard Big Bang theory come from, I'm going to say this without smiling, quantum fluctuations in the inflation field. What the hell? So in order to square the circle, because going backwards in time doesn't get down to a point, and you want a point for Big Bang, they've put in a flat plane and had everything expanding up to it in an enormous expansion in vector no time called inflation. And then in order to get that to work, they pretended it's a quantum field, and they call it the quantum field. And then there's going to be quantum fluctuations. And that's going to make some fluctuations in the universe instead of smoothing it out perfectly. So, I mean, I think, you know, we're in the range here of three layers of fantasy physics. Anyway, that's the standard theory. It's based on this pure fantasy physics. Okay, now here's some interesting data. So the CMB is typically describes the weak radiation field, but in fact, it's about 45 times more energetic than the background starlight field. So if you look at these are the fields, background fields in the intergalactic space here. So this is cosmic microwave background. Energy density 2.6 times 10 to the 5. Nothing else is anywhere like that. If you take the red stuff, the light stuff, that's the ultraviolet, the infrared, and this stuff here anyway. It's about 45 times down. You can work it out later anyway. So CMB is much more energetic than it's not just smoothed out starlight. That's the point. It's not smoothed out starlight. Okay, now let's go and explain where it's coming from. So you need to use the fact that the universe is filled with a noise of low-level gravitational waves arising from the inertial drag fields hypothesized in the explanation of the rotation curve, if you were that talk, and the relative motions of the massive black holes, the central galaxy, and other sources. And you can actually see this. You've only got to look at this wonderful picture, the Hubble Ultra Deep Field. It's the telescope, Hubble telescope, was very powerful. It can look back almost to the Big Bang. Well, except the Big Bang isn't there. So about one Hubble distance, about 13.8 billion light years. And they just pointed it at a dark part of the sky, a couple of arcs of sky, and left it running for a long, long time. A lot of money spent on that picture. And you've got a beautiful picture of the very, very distant universe. So it should come up now, but it may take a moment to come up because it takes a while to fill. There it is. This is the Hubble Ultra Deep Field. Okay, beautiful. We're looking at something. No, it's not going to. Yes, it has. Yes, you can zoom in and you can play around with this. I recommend you actually get one and play with it. It's wonderful. You can zoom in and you can see stuff. You can see, well, what can you see? I mean, here's what looks like a spiral galaxy, but it's all out of focus. There's something wrong with it. And what's this? These are all spiral galaxies too. They just look wrong. And there's something very funny up here. If I can find it quickly. Where is it? You see lots of these spiral galaxies. I've lost him. I've lost him. Yeah, there he is. Isn't that beautiful? I call this the face galaxy because it looks like a face. I'll come back to that. Well, the point is, you can see, oh, and there's some lovely galaxies here. But there's something wrong with them. They're all distorted. There's an enormous amount of optical distortion going on. The whole universe at this distance, by the time you get to one Hubble distance, but it's not quite one Hubble distance, you haven't got there. By the time you get to this kind of distance, it's blurred. It's just going wrong. It's going all over the place. And you can't see straight. Okay, there's a lot of gravitational waves around, a huge background noise of them. So let's go on now. So I recommend that you actually get hold of the Hubble Ultra Deep Field and play with it. So you get there's a link here. You can just download from this site here, and you want to take the biggest one, the 61 megabyte JPEG. That's what we're just looking at. And when I tell you something from the field, I'm going to give it intrinsic coordinates. So that's face galaxy. No, it's not face galaxy. It's coming up in a minute. So the face galaxy is, so 0.4 means 0.4 out of 10 across the way. And if it's negative, it means measured from the right. Okay, so these are, well, it's written here and you'll be able to read it out. Okay, so now I've assembled in the next slide 7 different, what seem to be obviously spiral galaxies with various sorts of distortion. So I'll come back and talk about these in a minute. So we just saw that's the face galaxy. And I think we saw one of these as well. No, maybe not. Okay. So these 2 galaxies here are interesting because I've chosen galaxies which are a long, long way away, but still obviously spiral galaxies. This one's obviously a spiral galaxy with some gravitational distortion. You can't really see it very clearly. And this one, even smaller, is probably a full-size spiral galaxy as well, but again, you can't really tell. So these 2 are interesting because if they are what they appear to be, full-size spiral galaxies of, say, 10 to the 5 light years diameter, and then they're measuring the image and knowing that the Hubble Ultra Deep Field has a linear size of 2.4 arc minutes, it can be calculated that this guy here is 11.10 to the 9 light years away and was formed a mere 2.7 times 10 to the 9 years after the Big Bang. And this one was formed within 700,000 years of the Big Bang. But if you know about standard model theory, it's much too early galaxies aren't supposed to have been born by then. They're not supposed to have been born for quite a few light years yet, quite a few years yet, quite a few 10 to the whatever, billion years. So these two examples are just a straightforward contradiction of the Big Bang Theory. You can just look at them, say, the Big Bang Theory is wrong. We are seeing too far. We shouldn't be able to see those guys. Okay. Anyway, we're not concerned with contradict the Big Bang Theory here. We're concerned with establishing a model with no Big Bang. Okay. So now this guy, the face galaxy, I'll tell you about that in a minute. And then on this row here, I picked out 4, I think they're obviously spiral galaxies, but they've all got distortion. You've got this one's having a very bad hair day here. So there's obviously something going on in the intervening space. And this guy's got some kind of bar coming across here, some kind of wavefront of gravitational distortion that's causing this lovely arm here to get a line in it. And these two have got other distortion. This is a toothpick galaxy. A lot of distortion like that appears. Okay. Go on. Okay, the face of this galaxy, that's this guy here, is interesting because you can actually turn it into a spiral galaxy by a simple bit of geometry, and you can see that what's happening is there's a gravitational soliton in between. So I don't know if it's going to work, but if with any luck I might be able to throw that up on the screen. But I got it ready here. Here it is. Right, there's the face galaxy. It's got a line of symmetry in the middle here. And there's another line of symmetry over here, not so obvious. But if you cut using those lines of symmetry and glue the outside bits together, you get a perfect spiral galaxy. So what's happening is the face galaxy is a spiral galaxy, but we're seeing it through the gravitational soliton that's put that distortion in. Okay, that worked. Let's see if we can get back. Yes, we've got back. Good. Okay, so the face galaxy is interesting because you can really actually show. I want to go back to full screen wherever it is. Because you can actually show the gravitational distortion, the gravitational field that's causing the distortion. Okay. And then you've got these 4 distorted spirals. Okay, so we've established by looking at the Hubble deep field and just using our eyes and not saying, oh, that's what's really there, and then we need some theory to explain these toothpick galaxies, which I tell you does exist. People look at it and they're working hard to explain all the things in there using standard theory. Bananas, anyway. There's no more bananas than standard cosmologists, never mind. Sorry, I shouldn't, some of you might be standard cosmologists. I shouldn't say that. Okay, so the background gravitational noise implies that light cannot travel more than a definite finite distance. In fact, from the pictures, it's obviously about 1 Hubble distance before it gets diverted significantly from its original direction. So it's like a fog. It gets moved around, it gets scattered. So there's an apparent boundary, like the apparent boundary in a fog where light's comprehensively scattered. So there's a natural horizon where light particles are randomized in intensity and direction, and I'll show you in a minute, in frequency as well, by the gravitational fog. This is what I called the dark horizon before. The CMB comes from the dark horizon. Observations of CMB carefully correct for all visible galaxies and other radiation source, and therefore select this apparent boundary. Light as seen by us travels in a typically random ways near the dark horizon. It's very unlikely to travel very far in any direction. It's sort of a random walk. So nearly all the light crossing the horizon from the far side and heading towards us has source within a region of depth about 1/3 Hubble distance, I'd say, behind the boundary. Now, this is the important part. This is the Resharma effect. Not everything that the standard cosmologists do is wrong, but they don't look at pictures. They look at theories and then see the pictures through the theory eyes and don't look. Light passing through a gravitational wave field exchanges energy with the field. And it's a special case of the Sachs-Wolfe effect. It's called the Resharma effect. And you can look in the Wikipedia to have it described for you. So the description is like this. So you think of a random gravitational wave field as a sequence of gravitational wells and hills, which vary over time. So a photon that goes down a gravitational well, then emerges after the well has become shallower, gains energy from the field because it gets pushed out and increases its frequency. And similarly, a photon entering a hill expends energy, but does not get all of it back if the hill becomes smaller before it exits. So the light's being randomized not just in direction and intensity, but by frequency as well. And so this is a perfect scenario for thermalization. So the region R we're talking about contains about 3 times 10 to the 10 galaxies, all emitting roughly thermally at about 3000 K. And after mixing and thermalization by the process we've described, the radiation emitted from R and I direction is a near perfect black body spectrum, again, of temperature about 3000 K. Now, the fog horizon is fixed with respect to us. It's a distance that we can see clearly. And therefore, it's part of our expanding frame. So the radiation is subject to cosmological redshift. The horizon is about 1 Hubble distance away, and the effect of this redshift, a little over Z equals 1000, is reduce the temperature of 3000 degrees, we've just seen, down to the observed CMB temperature model of about 2.7 K. And that's exactly what happens in the standard Big Bang model. But it's wrong. This is not the right description, because the energy coming to us in this way from the starlight field is not energetic enough because of the fact that it's coming from starlight. The factor about 45, the table that I got quoted from Long Air above. And to correct this, it's necessary to take account of the radiation coming from incoming sources in the contracting frame. So we've got stuff coming into us, as we saw before, and stuff going out. The bulk of this radiation is not subject to extreme blue shift and contributes at about the same temperature to that which is thermalized by the fog horizon. The energy boost from the incoming sources accounts for the high level of the energy in CMB compared with other extragalactic fields. Now, I've got to model this properly, and I haven't, and that's a future project. Maybe somebody's keen to do it for me. Anyway, so what you've got is this stuff that's coming over the horizon in the contracting frame, backlit lighting our dark horizon and making the CMB a nice strong field. So that's the cosmic microwave background. Okay, so now I'll stop after this and we'll have a chat. Oh, I was going to stop before the CMB, never mind. I haven't got anything else prepared much. Okay, so it's 1 Hubble distance away. So I suggest that the dark fog horizon where the CMB arises is called the Hubble horizon, in contrast to the infinitely distant DeSitter space horizon, which you got by using just the geometry, which I had in figure 3. Okay, so the crisis of physics is now easily explained. The 2 ways of determining Hubble's constant from nearby observations, e.g. supernovae, and from distant observations, properties of the CMB, give incompatible results with the experimental error. In this model, there's no crisis. The local measurements correspond to global curvature of the universe, determined by the cosmological constant, the curvature of the universe. And the distance observations correspond to the Hubble horizon caused by background gravitational disturbance. Although roughly the same, it's just coincidence. They're not really the same. They're out by about 20 or 30%. There's no theoretical reason to expect them to be the same. Okay, so one last point to make before we go away. I mentioned this Machian rest frame, which is sort of begging the question above Mach's theory, that in fact the Earth appears to be moving with respect to the CMB frame. But the Hubble horizon is a horizon. It's a virtual barrier caused by the behavior of light. So it depends on the observer. So it should be fixed with respect to the observer. And the apparent radiation, the CMB, should be perfectly isotropic. Like black body Hawking radiation, this is a horizon. Gibbons and Hawking's played with this, but it's much, much too small coming out of the sort of Hawking radiations, quantum stuff. You need real solid stuff. Okay, as I mentioned, that there's a dipole isotropy caused by the motion of the Earth. The explanation for this apparent contradiction is that the radiation takes a very long time to travel to us from the horizon, about 1 Hubble time. During this time, the motion of the Earth can have, and obviously has changed. So there's nothing funny going on here. The Earth just moved a bit, started to move compared with the horizon where it came. Okay, that's all I've prepared, and we'll go to questions. I'm going to stop halfway, but never mind.